Hello, my name is Matthias Gondan. I'm a professor for quantitative methods in psychology at the University of Innsbruck. This is a pre-recorded presentation for the virtual mathpsych meeting in 2024 on interaction contrasts for choice responses. We usually study behavior as a function of some experimental conditions. Throughout this presentation, I will denote these independent variables with script-style letters A, B, and so on. If we have a single independent variable, let's say strong and weak stimuli, we might observe some response times like those on the right. You can see that the response times for weak stimuli dominate those for strong stimuli. That is, the probability distributions are ordered with responses to weak stimuli slower than to strong stimuli. Things get a bit more complicated if we study behavior as a function of two variables, say A and B. So how much does your anger increase if you tear your favorite pair of pants? And if you talk to your students and they don't listen? And what happens to your anger if you experience both? In the statistics lecture, we usually put such things into a multiple regression and basically assume additive effects of our independent variables, b0 plus b1 times x1 plus b2 times x2, etc. But where is this plus coming from? And why are we even more excited when we see a statistical interaction which rules out additive effects? In a seminal work by Jim Townsend and Georgi Nozawa, they actually studied behavior as a function of two variables with other rules than plus for the integration of information from two sources. They also had a plus in a response time model. This is so-called serial exhaustive processing. In addition, they looked at the so-called race model with a minimum rule, the parallel exhaustive model with a maximum rule, and a mixture model, they used a different name for it, in which either one or the other channel is processed. And some more so-called coactive model, which I do not consider here. To formalize it a bit more, we need two assumptions. One is stochastic dominance. We have seen this already. Stochastic dominance says that processing times for weak stimuli, or let's say low salience components, dominate those for strong components because the processing times for weak salience components are larger in probability. Here I use the survivor function to illustrate this. That is the probability that the stimulus has not been processed by some time t. Of course, you can also flip the curve and consider the distribution function f, which is just 1 minus s. Note that we consider latent processing times here, which means that they cannot usually be observed. The other assumption is a more technical one. Selective influence states that we have done a good job in our experiment with factor A only influencing processing times dA and factor B only influencing processing times dB, but not vice versa. For simplicity of this presentation, I assume that the processing times are independent. On the right, you see an important paper by Zafarov, in which this assumption is relaxed in favor of conditional independence. I'll skip that one because for the present purposes, it basically means that we have more notational clutter in our formulas. And Zafarov has actually shown that the derivations also hold if the participants, for example, get tired over the course of the experiment, or if they sometimes concentrate more on one source than on the other. We can then start an experiment with a 2x2 factorial setup in which we combine weak and strong signals of two sources, resulting in the four conditions AB uppercase, AB lowercase, and the two mixed case conditions. We then consider the probability for a slow response under a race model in which the response time t is the minimum of the two processing times. T is large if the minimum is large. That implies both processing times dA and dB must be large. Under independence, the probability is the product, so that we get SAB is as A times as B using the notation with the survivor functions. We now apply this to the four conditions of our experiment, uppercase, uppercase, lowercase, lowercase, and so on, and then calculate the so-called survivor interaction which Townsend denoted as delta square S. Uppercase, uppercase, plus lowercase, lowercase, minus mixed, minus the other mixed. Using the results from above and applying the distributive law that we know from school, we get a product of two differences, S uppercase minus S lowercase for A, S uppercase minus S lowercase for B. By assumption, both differences are negative, such that the product is positive, which is theorem 1 of Townsend and Nozawa in 1995. For reasons which will become obvious below, it makes more sense to state this using the distribution functions. Then the interaction contrast is negative under the race model for all t. As mentioned before, Townsend and Nozawa also looked at other architectures. The results are summarized in the table on the right. We see, for example, for the serial exhaustive model, the interaction contrast is positive for small t and switches to negative for large t. We can now apply this to factorial experiments with different task instructions and investigate using the interaction contrast if participants process the components serially or in parallel, and what is the stopping rule. Note, however, that the theory is mute with respect to accuracy. In other words, the technique is mostly suited for lame tasks in which participants do not make mistakes. Recently, there has been made some progress with Little et al.'s paper on errored responses. Little et al. Investigate interaction contrast for conditional response time distribution. Conditional means that they consider the probability for fast responses in the subset of correct or wrong responses. Fast if correct, so to say. Fast if incorrect. What I'm more interested in here is fast and correct, fast and wrong. So I am happy if my pizza is delivered in time and it is the one that I have ordered. And I must add, it doesn't look promising. I have found a counterexample before that demonstrates that the problem cannot be solved in general. But it turns out that with a slightly more specific definition of stochastic dominance, we can proceed a bit further. Stochastic dominance now includes three properties. First, for strong stimuli, the subdistribution of correct processing times is higher than for weak stimuli. The reverse holds for the incorrect processing times. That one is trivial. On the right, you see the implications for a diffusion model with drift. In the second row, you see the densities. Here, we need a property that the subdensities cross only for correct processing times, whereas the subdensity for incorrect processing times are ordered. In the diffusion model, this can be shown to hold if the drift is positive. The last one is interesting as well, stating that the survivor functions are ordered. In the diffusion model, this holds if the starting point is not biased towards the incorrect boundary. All this sounds very technical, but it can be shown to hold for many of the canonical playgrounds that we usually use for response time modeling. Diffusion model, Poisson counters, you name it. The restriction is that we now consider only the subset of reasonable experiments in which the accuracy is, roughly speaking, above 50%. We can then show that the interaction contrast for the incorrect responses is positive under the race model, which is interesting. You see a derivation on the right, nothing really special. So this is for incorrect responses, the probability, and here we make an interaction contrast out of it and insert the sign that we derive from the assumption. So for the incorrect responses, it is positive. Remember that if stochastic dominance holds for the survivor functions, Townsend and Nozawa's theorem 1 still applies, just for the mixture of correct and incorrect responses lumped together. That theorem states that the overall interaction is negative, as we have seen before. The sum delta square f1 plus delta square f0 is thus negative. We have seen on the previous slide that delta square f0 is positive. Therefore, this term, delta square f1, must be even more negative under the race model for all t. We can therefore find a similar result as in the original theory, and in fact it's stronger because it's even more negative, so it should be more powerful. You can also see that if the assumption of non-crossing survivor function is violated, it doesn't work anymore. But you see on the right that for a mixture model with starting point variation shown here, it might work, though I think it's probably quite difficult to prove. For parallel exhaustive processing, we consider AND tasks in which both channels must pass in order to produce a correct response. And consistent with Theorem 2 in Townsend and Nozawa, the interaction contrast is positive for all t, also for the subdistributions of correct responses. For negative responses, so participants correctly reject a non-target, things get more complicated. This is done obviously an OR task in which failure in one channel is sufficient to reject a non-target. We could still figure out different scenarios in which the decision is made with a minimum rule, with a maximum rule, or the response is withheld in conflicting trials and the participant responds only if both channels fail. As illustrated on the right, we obtain distinct shapes for the interaction contrast for correct and incorrect responses in all these scenarios, and all the little arrows that are shown here can actually be proven. Unfortunately, in serial processing, the predictions are not that distinct. For small t, everything works fine. For large t, we cannot rely on the classical result of additivity of the mean response times anymore. So the interaction contrast might not change the sign anymore if the error rate gets too high. You can see this a little bit in the illustration on the right, that we obtain quite similar results for serial and parallel exhaustive models if the error rates are getting too high. And I think the sweet spot is probably found in scenarios with low but non-zero error rates in which the interaction contrast for serial processing still changes the sign. But with increasing error rates, the shape of the interaction for the serial exhaustive model converges to the one from the parallel exhaustive model. The mixture model is easy again, but it gets complicated if we consider the negative responses. I can elaborate this on request. In sum, things are more complicated and we need to design our experiments carefully to obtain a sensible amount of incorrect responses, say 20%, for example, and we should also use a priori information from the task instruction. Here's a setup for a memory scanning experiment, so a very demanding task that entails non-negligible error rates. And just to point your attention, I have mapped the 2x2 design of our factorial setup to a 1x4 design in which the uppercase A and the uppercase lowercase a and b as well denote a different number of distractor items in our memory set. We can do this with visual search tasks. We can run experiments with cool stimuli like mental rotation tasks. You can see on the right serial rotation along an allocentric coordinate system, and in the lower panel kind of a parallel rotation around two axes, and it should be possible to distinguish this based on the interaction of the response time distributions. That is actually a true story I recently experienced, in which the policeman used a minimum rule for the combination of two fines. Thanks for listening, and if you have questions, use the forum or write me an email. Thank you.